Ah, the joy, the bliss, the beauty. The antenna points itself automatically to the target, be it terrestrial or space-bound. The antenna rotator. Now you can concentrate on the radio contact with the satellite from the comfort of your workshop or shed.
Hello and welcome back. In today's episode I'm going to present you a antenna controller made with an Arduino and stepper motors. This one is for stepper motors. I also made an antenna controller for AC or DC motors with feedback potentiometers. This project, because it employs stepper motors, do not have a feedback mechanism, and we are only counting for the stepper motors to do their job and to position themselves where we want. So it is made out of an Arduino, an LCD display, one encoder and two encoders, one stepper motor here for azimuth and one stepper here for elevation. You also will see the end of the line switches for the elevation, and there is an end of the line switch for azimuth here also. Well, how it works? This controller works with computer command, so you can use the good old Orbitron to command it with a USB cable or other satellite tracking software which uses EasyCom1 or EasyCom2 protocol. EasyCom1 transmits data to the controller, and EasyCom2 also reads back the antenna position back on the screen. Right now we are doing some tracking, some satellite tracking with Orbitron. You see the coordinates displayed on Orbitron are also displayed here on the screen, and this part, azimuth elevation, is the antenna position, and the other part is the target position. CD means command. This is what I chose to name it, command, but it could also be target, TG, TJ, yeah, whatever. And equals means that the position are achieved, the target is achieved, and when the antenna moves you will notice little arrows pointing in the direction of movement, just like that. This is an indication of movement, but as I said, the stepper motors do not have an internal feedback mechanism. They do not tell us where they are. They can only move precisely from one point or another. So you can see that the elevation is pretty much correct, 17 degrees, and the azimuth around 335 precisely, 34 now. Okay, for Orbitron to be able to command via USB this controller needs a plug-in, this one, which I will link down in the video description in the project page. And I will just leave you on time lapse to see how it tracks the satellite. Some shots during the production phase. Just a regular connection box, plastic connection box with an Arduino inside, and a lot of wires, two encoders, display, drivers, and stepper motors. Well, let me demonstrate now how you can manually point the antenna in the desired direction. You must remember that at any moment the controller, Arduino, waits for computer command at any moment. So the computer command for satellite tracking is the main objective of this project. If you want to move the antenna manually, you depress the azimuth encoder you see on the screen there is an asterisk, which means that now the controller is in a manual input state. It doesn't want to receive computer command now. And now you can adjust with the help of the azimuth encoder the azimuth you want the antenna to go to. See? Let's say 180. And with the help of the elevation encoder, let's say 45 degrees. Now you depress the azimuth again. And bam, the antenna starts to rotate. Okay. There's another feature. If at the end of your satellite hunting session wants to point the antenna in a particular direction, for example, where the wind load is minimum, or you just want the antenna to point somewhere funny, you just have to press the elevation encoder like that, and you will see on the screen a symbol which means that the antenna goes to the parking position, which is pre-programmed in the software, and I'll show you in a minute how to do it. In my case, I pre-programmed 120 degrees and 0 elevation. Now let's go a little deeper in detail to understand profoundly how this thing works. So let's begin with the initiation. At startup, the controller doesn't know where the antenna is. As I said, the stepper motors do not tell us where they are. They only move precisely from one point to another. So at the start, the controller doesn't know where the antenna is. It can be at 180 like now, it can be at 0, at 90, it doesn't know. So for that, it assumes the worst case scenario. It assumes the antenna is all the way back in azimuth and in elevation, and gives the command to move slowly towards 0, because at 0 we have a switch, an end of the line switch, and when the antenna touches this switch, we know precisely it hits 0, and from this point on we can calculate its further movement. So as if I reset the controller, we have a splash screen, and you can see it assumes it is all the way around, and it moves it slowly towards the 0 position. It already reached 0 in elevation, the end switch is depressed, and when it reaches 0 in azimuth, look, bam, it stopped, and we have 0. From this point on, the controller knows precisely where the antenna is and will move it according to our command. Let's go deeper to understand how the code works. The code is everything. So, starting with the beginning, we have few libraries which must be installed. If you don't know how to install them, you go right there, Library Manager, and you search, for example, wire.h. I will show you later on in much more details. And the thing you are interested in the code is this section here. As we scroll down, we found this section here, parameters to modify according to your motors. So the code must know the azimuth step pulses per 360 degrees. How many pulses, how many steps the motor does for full turn. How do we know that? Well, it's complicated, and we can either calculate if we know the values, or we can use a little sketch that I made which actually counts those pulses and outputs them on the LCD. So we need this number to be written here in the code, and once you do that, it's done forever. You don't have to do it again. I'll show you how to count those steps. for azimuth and elevation. The next thing is azimuth and elevation coordinates for antenna parking. So here you can input your azimuth and elevation coordinate where you want the antenna to go when you press the elevation button. I just made 120 degrees to 0, but you can point to any direction you want. The next parameter, important parameter, is the speed. The speed, as I will explain later in this video, is a tricky thing with stepper motors. So watch the video and you will understand what I mean. It also depends on microstepping. I will explain that in a minute. The acceleration, I set 0.8 of the speed. So what this software does, it accelerates, it ramps up the speed of the antenna, then it rotates, and in the proximity of the target it slows down, it decelerates. So if the acceleration is closer to the speed value, this acceleration is much more steeper. If you put here, for example, 1 times the speed, so acceleration equals the speed, there will be no acceleration. There will be just a sudden start and a sudden stop of the antenna. Yeah, so you got the point. Right now I'm going to show you how you count the steps with another software. This is the software, and you will find everything in the project page on the web, which I will attach in the video description. Here we have a small software which moves the antenna towards 0 and then moves it towards the other end switch and counts the pulses and displays them on the LCD. Right, so I cleared the screen so you can see how I will upload the code. And you will see the antenna moving slowly towards 0. You see? And once it reached the end point, you will see on the screen that the elevation reached limit 1. Azimuth doesn't yet reach limit 1. But the elevation already started to move towards limit 2. Now the azimuth reached limit 1 and moves back. You can see on the screen, azimuth reached limit 1, elevation limit 1. Bam! Elevation reached limit 2. Look, yes, it depressed the end switch, and this is the number of steps it takes the elevation to do a full movement. Now the azimuth is moving towards the other end switch. It's better to do this process several times to be sure that the motors move consistently, and I repeated this process again. Now you will see the azimuth will reach the end point. Bam! And on the screen we have the values read again. We write down these values and input them in the main code. And upload the new code to Arduino. That's it. The code's done, and the antenna will start moving towards 0 now. Bam! We have 0, 0 on the screen. Okay? From this point on, the controller is ready. If you want to test this project in the phase of development, that's very easy. You just open a serial monitor and type a command like that using caps lock. That's mandatory. As and a coordinate, for example 90, pause, L, for example 30. Bam! The coordinates are instantly sent on the screen, and you will see the antenna moving. Excellent! Look. If you want to know the antenna position, you just type as pos L, and the antenna will reply, a controller will reply with the coordinates in this format. And this is the EasyCom protocol. This is how it works. It's very easy. Let's do it again. Azimuth 180, elevation, let's say 90. (180) and 90. This is how the EasyCom protocol works. So it's very, very easy. You just type as and coordinates, for example, 240, elevation, let's say 10, enter. The controller does not respond, doesn't have to respond. So it just moved to 10 and 240. Okay. Now let me show you another software which is much more powerful than Orbitron, which is called PST Rotator. You have to pay for a license. You have to purchase a license for it, but it is very cheap. It's worth it because it is a very powerful tracking software. Right, so this software displays the antenna position. As you can see, is 0 and 0. This is the antenna position and this is the command. Let's see how you set up this software, because it is rather tricky to set it right. It is very powerful. This is why it have so much settings. So first, communication, as L, azimuth elevation, COM port, and you select your own COM port, in my case COM3. That's it for communication. Then setup, and you go to elevation azimuth controller. You scroll all the way down until you find this thing, K3NG EasyCom. This is what you will select, K3NG EasyCom. There's another EasyCom here, EasyCom ST1 Fox Delta, but you don't want this one. You just want K3NG EasyCom. So next thing, my location. Very important for the software to know where you are in order to track the satellite correctly for you. This is my position. Next, 3 dB beam width is just how wide this picture here is around the antenna position. Rotor refresh rate, I set mine to 1 second. What does it mean? It means how often the antenna position is refreshed on this screen. Tracker refresh rate is how often the satellite position is refreshed. The satellite moves rather slowly, so you don't want to refresh it too often. 3 seconds is fine, even 10 seconds is absolutely fine. The rotor refresh rate, on the other hand, is good to be at 1 second, because you want the screen to show the position as accurate as possible. Next thing, this one you don't want to care. Parking setup. Parking setup, as I explained in the controller setting, is where you want the antenna to be parked when you press this button here, park. I pressed it and bam, the coordinates is 270, and you will see the controller moves directly to 270. Yeah, that's it. Well, next thing, satellite tracking setup. This thing tells the controller what to do when a satellite is below horizon. For example, to stop tracking satellites below horizon. Because what does it mean? It means that it only moves in azimuth because elevation is negative, and it's useless to do that. And position change means at each degree, for example, the software outputs the new position. If you select, for example, 10 degrees, the software will not output the satellite position unless it changes for 10 degrees. Next thing, you will play with this thing if you want to. If your rotator supports 180 degrees, and I will strongly advise you to have a 180 degrees elevation rotor, you check this thing here. I will uncheck it because mine has only a 90 degrees. This other thing interesting here, you don't want to, it's not important here to mess with them. Start in manual mode or start in tracking mode. The software starts like that when you first install it, but if you want to track satellites, you must go here, setup, and check satellite tracking, and bam, it offers to update the telemetry, the satellite telemetry. And here you can program some satellites you want to track. If you go to tracker, you must check satellites, otherwise it will track other things, and this thing you don't want to change. That's all about the setup, and the rest you can play with. There are interesting elements, and if you want to actually track those satellites, you click here, tracking, and the software starts to transmit towards the controller the satellite position. Let's see if we have a satellite which is nothing above our heads right now. But the software is very, very nice because it will tell you how long until the satellite will be above your head, the satellite parameters, it is capable to adjust the frequency of your transceiver, and so on. On the other hand, you can point the antenna manually with this software. For example, if I click 150, bam, the antenna goes to 150, and you see here the coordinates on the screen. Let's point it where you can see the elevation to 300. The antenna has this kind of interruptions because it talks back to the computer. So these interruptions appear when the controller talks back to the computer. It's not a problem. So let's move up in the elevation, 45. The coordinates appear on the screen and the antenna moves to 45. Let's move it to 90. Bam. Nice. Let's move it to 10, 15. Well, I forgot to mention, when the antenna is moving, if the antenna is moving, it doesn't accept any other commands. So the controller is only focused to moving the antenna towards the new position. Only after it reached the new position, it will accept another command. So now I will tell it to go to 14, and it will go to 14. If I tell it to go to 350, and then I will tell it to go to 60, it won't accept 60 because it is already moving to 350. Only now can I move it to 60. All right. So let's park it, and let's move towards the new explanation to go further in-depth explanation with how this controller works. You will notice in the code on the screen that it requires few libraries: liquid crystal, wire, and axial step library. At first you will get an error, the library is missing. In order to install the library, you click here on the library manager, you search exactly as the name here is written, so Whoa, and this is the one. Axial stepper by mic. Not axial stepper with distance blah blah blah, because only these letters are here. Axial stepper, identical, okay? By mic. You click install. You search for liquid crystal _ I2C. Liquid crystal, that's the one. Liquid crystal I2C by Frank. This is one you should install. You click install, bam, and it is installed. Then the code will compile without errors, and you will be able to upload it to the Arduino. Now let me explain in detail how the program works. First of all, I've made a development board, a breadboard, like this one, which I strongly advise you to do prior to assemble everything into a nice box and something, because this is your opportunity to troubleshoot any inconvenience that it might occur, and it will occur. Yes, so when everything works as you want on the bench, spread out like that, then you can put it in the box and hope it will work just the same. So this is the exploded composition, just as in the electric diagram that I present you here. You take a good look at it. Okay, you saw it. Now I will take it off the screen and I will show you a small program I devised to count the steps of the stepper motors. This is, as you can see, the elevation motor and the azimuth motor. All right, let me zoom in a little. Right. So exactly as in the electric diagram. So what we have here, we have the drivers, the stepper motors, the limit switches, as you saw there in the electric diagrams. And let me explain step by step what everything does. You must understand that when the antenna rotates, it at one point reaches 0 or all the other way around, 360 degrees, and it has to stop, otherwise it will turn forever and wrap the cables of the antenna around the pole until they break, or the inside of the rotator will spoon around the pole and will break eventually. So we have those end switches. Those end switches don't act directly on the motor, but they are read by the microcontroller. So they are read in the software, not directly hardware linked to the motor, because that's impossible. It is possible with DC motors and AC motors, but not with the steppers. The steppers and the end switches must be read by the microcontroller and decide what to do when you hit the end. So these are regular switches for the elevation that I installed here. They are the most unloved and ugly switches I could find, and I will repurpose them for this project. And this is a nice one. I salvaged it from a printer. A printer is a treasure trove of goodies, motors, switches, gears, everything. You should salvage old printers and scavenge the insides. All right, so I wrote a little code which turns the motor around. They are not installed with gears and something, and I will simulate what it does. So what the software does, it turns the motor around, and at some point it hits the end switch, the azimuth. It hits the 0 degree or the 359 degree. All right, and the same does the elevation. It it rotates, and at one point when it lowers the boom, it hits the 0 degrees, or all the way up hits the 90 degree. Okay, what this code does is it moves both motors towards 0, and once each motor hits 0, will move the other way around to the other end, 360 respectively 90, and they will completely stop. But on the display we will see limit 1, limit 2, and the number of steps, not the degrees, the number of steps the motor does between those two limits. The number of steps are essential to be inserted in the original code, because the number of steps divided by 360 determine the step per degree the software use to point the antenna precisely. Let's turn it on and see what it does. So I hit the reset on my Arduino. The motors will start spinning. On the display, azimuth elevation is blank because I haven't reached any sort of limit. Let's suppose the azimuth hits 0. Bam, it hits 0, it turns around. Yes, and L1, limit 1 is achieved for azimuth. Let's suppose elevation hits 0. Limit 1 in elevation is achieved, and it starts turning the other way around. Let's suppose azimuth hits 360 and it stops, and we have the number of steps which is necessary for it to perform the whole circle. Bam, the elevation hit 90 degrees and it stops also, and we have here the number of steps it needed to perform the whole movement. So these numbers, you write them down and you input them in the code for the antenna controller. As you can see, I took the benefit of the enable pin, and once the enable is high, the whole driver stops working and the coils are deactivated. The same goes for the elevation. Right now the encoders are not used in this code. Let me explain the phenomenon I was talking about earlier, which is the stepper motor losing step or jumping steps. As I said, the stepper motors are great for precision movement because they can position themselves precisely, but because in my project and a lot of other projects employing stepper motors, we do not have an actual feedback mechanism to independently determine the motor position. We are only counting the steps and hope the motor goes where the steps are. But if there some phenomenon intervene, like friction, like some sort of blockage in the mechanism, the motor receives the steps, but sometimes somehow it cannot performs like that. Look at that, what happens. So it receives the pulses, it receives the steps, but bam, something mechanically happened and the motor is jammed. In this case we lost the track of the position. We've lost the position. The position is unaligned, is offset. We know in the software where the motor should be, but it isn't there physically, actually, really it isn't there, because it skipped steps, and we cannot determine that ever, and we cannot know the motor is offset. But the mechanism that can be used to counteract this phenomenon is, from time to time, or at least at startup, obviously this happens, yeah, the motor goes to the home position. As I demonstrated, the motors go to 0. We know there is 0, and then from this point on we count steps. If in time somehow the motor becomes, the antenna becomes offset with the true position. Only thing we can do, we can reset the microcontroller. It goes, moves the antenna back to home position and realigns. And the same thing can happen when the motor jumps step. So I've demonstrated when it skips steps, yeah, because I can stop it with this plier. But sometimes it can jump steps, or it moves faster than desired. Let me see if I can do that. Yes, I can. Yeah, so I moved it faster than desired. So it also becomes offset, unaligned, and the only countermeasure is to reset the microcontroller. The antenna goes back to home position, 0, initialize, and then move on and get on with our life. Yeah. Right, so you saw how it worked, how beautiful the magic happens, the antenna pointing, everything. Computer control, manual control, display, yeah, antenna feedback on the computer screen stuff. But we must have a deeper understanding about how actually a stepper motor works, and this particular driver TB6600 works, and microstepping and pulses and everything, pins, enable, pulse direction, power supply, everything. Yeah, so I've made this demonstration. I've connected the driver just as in the electrical diagram with this small stepper motor. It's not a NEMA something. It has a reduction gear inside. It would have been ideal not to have that and to have just the bare motor to witness precisely one-to-one how it rotates. But since this is what I have, this is what I show you. And I've wired the board. I will repeat the electrical diagram. So of course, first is the power supply, which is a 9 volt, in my case, a 9 volt adapter, and a small plug here. Yeah, let's put it in shot right there. Next, the coils A plus, A minus, B plus, B minus. Yeah, you have to identify those in your motor, and the easiest way to identify, you have 4 wires, and you just use your ohm meter to measure the continuity between some of those wires, and you have continuity between 2 pairs, obviously. So those are the wires, the A and B wires, and you wire them like that. If by hazard the motor doesn't turn, makes noises, hits up, then you have to just rotate 2 of the wires. Another thing is, if by hazard the motor rotates in the opposite direction than the one you desire, even if in the code you can alter the direction, but you must have a default direction at the beginning, and if it rotates in the opposite direction, you just reverse all the 4 wires upside down like that. All the 4 wires in the same order, just upside down, and the motor will rotate in the opposite direction by default. The next important pins, connectors, are the pulse. Pull comes from pulse, plus and minus, direction plus and minus, and enable. You see here we have signal. Yeah, so these signals go to Arduino, but it's simpler than that, because every minus goes to ground, and I've just jumped these green jumpers. Bam bam, are jumped between minuses and to the common ground at the power supply, so everything must have a common ground. So jump ground, 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 and then with this green one to the Arduino ground. Yeah, of course. And we are left with only 3 pins: pulse, direction, and enable plus. Pulse plus, direction plus, and enable plus. Yeah. Pulse plus is wired to the specific pin of the Arduino. Direction plus is wired to the specific pin of the Arduino. Yeah, if you want me to, I will wire it correctly here. Yep. But later on I'll make a little demonstration. And the enable pin, which I will talk about it in a second. I've made a very short and simple sketch which makes the motor to run continuously in one direction, just for the purpose of this demonstration. And I can alter the speed by typing in the speed I desire in the serial monitor. Right now Arduino is not connected, power supply to the driver is not connected. I will start the thing right now. So I will connect the driver first to see what happens. One more thing, I've connected some LEDs on the some appropriate connectors. One LED is connected to the coil A and one LED is connected to the coil B of the motor, so we can see how the coils are activated and if they are or not activated. And one LED is connected to the enable pin, because I will talk about it in a second. It is important. So I'll connect the driver. Driver is connected. Nothing happened. All right. I'll connect the Arduino. And we see on the laptop screen, yeah, enter speed. Right now it started to rotate at a default speed, and we can see the LEDs, the witnesses of the coils are lit. Yeah, let's try to input a speed. Let's try to input the speed 100. Bam. You see the LEDs kind of blinking. Yeah, the motor is buzzing because the steps, you know, it turns in steps. So I can almost feel the steps it makes. Yeah, if I type in an even smaller speed, let's say 50, if 50 means 50 pulses per second, I can already see the LEDs blinking. The speed is slow. Yeah, come on, focus. Yeah, let's type an even smaller speed, let's say 10 pulses per second. Look at that. Look at that. And the motor is spinning. I can hear it. You can hear it. It's clicking. Those are the steps. All right. On the other hand, we should take... okay, let's go further. And I'll come back to this idea. So, what is the slowest speed? 0, of course, or 1. Let's type 1. So it's 1 step per second. Look at that. Look at the coils activated. And I'll fast forward a little bit. Yeah, so it rotates 1 step per second, which is marvelous. Yeah, I can even type 0. So 0 steps per second means actually stop. So what do we see? We see that a coil is not activated and one coil is permanently activated. So what does it mean? It means that one of the coils, but it depends on the state it catches the driver. It can catch a state when both coils are activated or one of the coils is activated. But always a coil will be activated. What does it mean? It means that one of the windings is connected to the DC power supply, to this one, the DC here, power supply, so it is constantly electrified and it just heats up. That's all it does. A coil heats up because it is subjected to a DC current. So for a longer period of time you should be aware when the motor stops, a coil is always activated or both, and the motor will heat up. We'll talk about this later, how we can prevent this. Let's input a higher speed, let's say 400. Bam. Oh, it rotates nicely. You can see the LEDs are, they blink, but we can no longer see them blinking. Let's input 500. Even faster. Let's input 800. Oh, what do we see? The motor stops spinning and it buzzes and it heats up. All it does, it heats up and buzzes and stops turning. Why does it do that? Because the pulses are coming in so fast that the stepper is no longer capable in this short amount of pulse to actually turn physically. So the inertia of the rotor prevents it from turning from such a short pulse at higher speed. So we have 800 steps per second. Let's, if I can go even higher, 150 or 1500 steps. It's just the same. It just buzzes on a higher pitch. That's all. 2000. That's all. It's the same. It buzzes at a higher pitch, but it never rotates. So what have I noticed? That it turns to 500? Yes. Let's see if it turns to 600. No. So let's go in between 550. Barely, but it's not the correct speed and it vibrates very powerful. Yeah, you can hear it. So 550, 540. 540. So 540, let's go 545. 545. No. 544. No. 543. No. 542. No. 541. No. So 540 is the maximum speed this motor can turn at. Yes? Alright. But now I can talk about micro stepping, because you can see that this driver has this inscription here, micro step driver. So we can do micro stepping. What does this mean? It means that it takes the pulses, the input pulses, yes, here from, and what does it do? It divides them and smooths the movement of the stepper motor. So for example, you can see here that it can do, for example, now we have one micro stepping. One means one pulse, one step. All right, and for that we have a dip switch, which is should be positioned like that. Look at that. Right. And if I position like that, not connected, not connected, so on, like that. So on. Oops. It just stopped because it doesn't do anything. So let's go again to one, micro stepping one, which is on, off. It rotates normally if at the maximum speed it can do right now, 540 steps per second. What actually happens is that the motor, the stepper motor inside this assembly moves faster, but because it has a reduction gear, actually what we see here at the output shaft is a lower speed, but the internal motor rotates at 540. the actual rotation here is, I don't know, slower, obviously. It has a rotation gear ratio at about 1 to 14, something like that. Yeah. So the microstepping. What does the microstepping do? Obviously, it slows down the movement. So if I activate this thing, 400, not for this is bullshit, pulses per revolution. Let's suppose what happens here with this inscription. Let me explain. So this is important. Microstepping 1. 1 means 1 to 1. 1 pulse, 1 step. This is just, I don't know why they wrote this here. Let's suppose we have a motor which has 200 pulses per revolution. All right. We must look at this column here. So let's move to microstepping 2A. Actually divides by 2 the pulses. So it takes 2 pulses to move 1 step. And for that we have on, off, on. What happened is that it moves slower. Yes. So if I just increase the speed in the software, let's go to 1000. It can do 1000 easily, all right? And also it smooths the movement. It's not choppy anymore. Or let's say 100. It moves slower, so half the speed. It moves to 50 pulses per second. Let's go 2000. It doesn't work at 2000. It buzzes and it hits and it stops because it doesn't work at 2000. Why it doesn't work? Because all it does is divide the pulses to the steps. Yeah, so it takes normally it takes 1 step, 1 pulse, 1 pulse, 1 step. Now it takes 2 pulses, 1 step. So it doesn't work for more than 2 times 540. Yeah, so let's put 1080. It barely moves. So I can go as high as 1040. If I go 1050, it shouldn't work. Yeah, it does. So this demonstrates that the microstepping actually helps smooth the movement. All right, let's go further. Let's go microstepping 4 times. Yes, on, off, off, on, off, off. The speeds is a quarter of the initial speed. Yes, so we should be able to input 4 times 540. This means 2200. 2200. Can't do. I was expecting. Let's go 2000. It can do. 2100. Yes, can do. I hope I made myself clear with the microstepping thing. If you want the motor to run smoothly, it is indicated to run it at higher pulses but at higher microstepping. So I recommend using microstepping 2 or 4. Yeah, this smooths out the movement of the motor. The next 3 dip switches are for, look here, for the current limit. So this little driver can also do the current limit for the motor. If you feel like your motor can draw a lot of current and heat, you can limit the current consumption. For this motor, for example, it draws very little amperes. The smaller amount of limitation is 0.5 amperes for 500 milliamperes. So 0.5 amperes is on for the last 3 switches, as you can see.
If you feel like your motor should draw more current, feel free to position these switches to the appropriate setting, but I recommend you do set those switches to limit the current, because sometimes it can jam. Let's say by hazard the motor jams and it draws more current than normally, and you don't want it to fry, to heat up until it smokes. So that's about it in terms of microstepping. Let's speak about the direction. The direction can be adjusted. You see here we have two pins. We have a pulse pin and a direction pin. The software manages the direction. How does it do that? If I type minus 1000, it goes in the opposite direction. All right, so you change the direction in the code with a minus. Let's go back to 1000. It moves normally. But actually what happens? It happens that the direction pin, you see, if the direction pin is not connected, it moves in one direction. If it is connected to plus, it moves in the correct direction, and if not, it moves in the opposite direction. So it has some sort of pull down resistor inside, some pull down element, and it is pulled to minus. And if we pull it to plus, it moves in the correct direction. But this thing is managed by the software. Minus 1000, actually Arduino pulls down this pin and the driver understands and changes direction. Another thing, if I input a 0, speed 0, you see we have LEDs. We have LEDs which signify the energizing of the coils. If we input 0, we should not have the coils energized, but we do. We do have one coil. It depends on the state. The driver is surprised in the moment of the 0 speed input. So we no longer have pulses here. Actually what happens is we no longer have pulses here, but this driver remains in the last state it lost the pulses. So one coil is always activated, as I mentioned at the beginning of the presentation. If your application implies a motor which spins most of the time or all of the time, that's fine. This will never happen. So one coil will never be energized in DC for a long period of time for it to heat up. But in the case of our antenna rotator, well, the antenna moves until it aligns with the target. But after that, actually the antenna and the motor moves very little. It moves a little, it stops a lot, moves a little, stops a lot, and this puts more heat to the motor. And the enable pin comes in handy now. Well, if one coil is always activated, it is hard to turn the motor by force. So if the coils are not activated at all, you can turn the motor relatively freely. But if a coil is activated, it acts like a brake. But if we don't want that, and we don't generally want the motor to act like a brake and have a coil permanently activated, and this is when the enable pin comes in. So if I connect enable minus is to ground, but if I connect enable plus to plus, the coils are deactivated. Yeah. So by connecting the enable to plus and minus, actually we disable the driver and we no longer have the coils activated. Right now, bam, you have the coil activated even if the motor is not spinning. Let's spin the motor and activate the enable. You see, the motor stops. The driver itself is disabled. So to disable the driver, you have to connect minus to minus and plus to plus. And this disables the driver. If you do not connect the enable at all, like that, at all, it doesn't matter, the motor does its job even if you stop it in the code. You see, it stopped now in the code and both coils are activated because this is how the driver was surprised. But if I activate the enable pin, it frees free the motor. And the motor no longer heats up when stationary, which is very important. So if I touch enable, bam, it stops. If I let it go, it spins. In the code, I took care of this enable pin, and the microcontroller Arduino and the code take into account that when the antenna is aligned with the target, the pin, actually what it does, the code, when the antenna is aligned with the target, it inputs speed 0, and whoa, by hazard, right now when I input speed 0, the driver was surprised with no coils energized. But let's put it again, and 0, and bam, it caught a coil energized. So I take that into account into the code, and when I stop the antenna, so it was spinning, bam, it aligned with the target, bam, and I also activate the disable pin. When it needs to realign with the target, I let go the enable, I rotate, stop, activate the enable. This is how the code works, and it will prevent the motor from hitting when stationary. So let's summarize what I just explained. First, the motor, the stepper motor, is a precious one. So you must take into account that if the speed, sometimes the speed is too low, it doesn't turn. If the speed is too high, it doesn't turn. But what does it do? It heats up. It always heats up. So you must be careful. When it heats up and doesn't turn, you must work with the speed. You must work with the micro-stepping.
Houston, Eagle has landed. Roger, Tranquility. We copy you on the ground.